The foundational block of every complex model is a system of equations. Although their mathematical notation is precise and powerful, it becomes visually confusing once our model scales from a couple of equations to thousands of equations. The elegant and convenient way is to categorize equations as components and connect them through appropriate connectors. Modelica offers a graphical connection editor to build and connect models in an intuitive manner. In today's session, we will revisit our previous model for heating and cooling of a metal ball and build them using the components from Modelica standard library in a visually intuitive manner. Welcome to Simulation Workshop, where we learn to build worlds through equations. In our previous video, we built a simple model for simulating the heating and cooling of a metal ball using the text interface of Modelica Connection Editor. We defined the parameters using the standard types in Modelica, and we defined the equations connecting them. And we simulated the setup for 2100 seconds to get the results. This is robust and gives accurate results. But wouldn't it be nice if the same model can be represented as a combination of multiple components interacting with each other? We have the ball with a surface area and volume, which interacts with surrounding air through convection, where heat transfer coefficient and the temperature of air can be controlled using external signals. Modelica standard library facilitates the development of such complex models using built-in components. It has an extensive library of 1000+ components in the latest version. These components are categorized into several different subsystems. Some of them are causal connections where we have clear cause to effect distinction, and some of them are acausal models. And these are further categorized into different domains such as electrical, magnetic, mechanics, etc. The combination and interconnectability of these different domains help us to build complex models with ease. For example, a pump model receives its input signal or the input energy in the form of electricity. This is later converted into magnetic energy in the motor windings. The magnetic energy is later converted into shaft rotation, and then it further facilitates the pressure increase of the fluid that it conveys. So a combination of electrical, magnetic, mechanics, fluid, and media libraries are required to effectively model this complete motor plus pump model. Now let's see how we can make use of Modelica standard library components for our model. Before we go further, let's recap the problem statement. In our previous video, we simulated the heating and cooling of a metal ball starting from 25 degrees Celsius and subject to an airstream at 200 degrees Celsius flowing at 20 meters per second. This heating is continued for 900 seconds and later it is cooled by a cold airstream at 20 degrees Celsius flowing at 10 meters per second. This is continued for 1200 seconds. Our objective was to find out what is the maximum temperature attained by the body and what is the final temperature after this process. We used two governing equations, one connecting the rate of change of temperature with the heat transfer, and the one connecting the heat transfer with the temperature difference between the ball and the surrounding air. This is known as Newton's law of cooling. Also, we used some basic equations to calculate the volume and surface area of the ball, and also we used density times volume for calculating the mass. Also, from various sources, we found the parameters that are necessary for calculating these values, such as the density, specific capacity, etc. Now, we will be using the components from thermal library in Modelica standard library. We will have the thermal subsection in Modelica standard library, where we have another section called heat transfer. We have two components, heat capacitor and convection, and we will be taking one source to represent a prescribed temperature value. So this will represent our airstream in the model. Also, we will take some components from blocks, which are step, which is used for changing the values at a specific instance. and we will use the product function from math, which will multiply two values and return the result of it. Now let's see how these are connected to our model. The heat capacitor can store energy and that will change the temperature, so it can represent the ball. The convection model can represent the interface between ball and the air surrounding it. Then the prescribed temperature can provide the air temperature that can be changed using a step value. Also, the product can be used to multiply surface area with heat transfer coefficient. Now, the thermal components are mostly acausal, whereas the components from the block are mostly causal. So if you take, for example, the product, we are inputting two numbers and the output is the product of them. So the cause and effect are very clear here. Whereas in case of a heat capacitor, the change of temperature and the heat transfer are mutually connected, and we cannot clearly say which is the cause and which is the effect. Now, these can be connected using different type of connectors that we will cover while we do the live session. Now, before we go into building the model, let's get familiarized with these components in little more detail. Heat capacitor carries the equation Q is equal to M times Cp times dt by dt. That is, the rate of heat transfer is proportional to the rate of change of temperature. And this takes C, that is the heat capacity, as a parameter, which is the product of mass and specific heat capacity. Also, it can interact with surroundings using a heat port. A heat port has two parameters, that is the Q flow and the temperature. So this will facilitate the thermal connection between different components. Also, we can specify a starting temperature for this heat capacitor. Convection component has two heat ports, one representing the solid interface, that is the surface of our heat capacitor, and the second one indicating the fluid interface, that is the surrounding air. It takes one input, that is the convective conductance, which represents in our Newton's law of cooling the product of heat transfer coefficient and surface area. So this convection represents a generic convection surface where the surface area is an input parameter. So the difference between this heat capacity specified here and the convective conductance specified here is that this can be changed during the simulation because we are connecting it as an input, not as a parameter. Now we have a prescribed temperature which can take a real value in Kelvin as a temperature, and it can convert that as the temperature of a heat port. So this particular component can take any amount of heat energy without changing the temperature. So this is ideal for representing our air, which does not change the temperature with respect to the heating or cooling. And the temperature can be changed using the input real number. Moving to the block section, we have a step value, which can take three parameters such as start time, offset, and height. So start time is the point in time when the value of the step function changes. Offset is the initial value that the component will return, and offset plus height is the value that the component will return after the time exceeds start time. Product is the simple mathematical multiplication. It takes two numbers as inputs and multiplies them and returns the output as a real number. So this can be used for performing mathematical preprocessing calculations. Last but not least, we have a function to convert degree Celsius to Kelvin. This performs a simple conversion using the constant 273.15 between degree Celsius and Kelvin, whereas it takes a real number in degree Celsius and converts to Kelvin. So this is convenient because it really conveys why we are adding this number. Now let's try how we can build the model. We have the conceptual model. We have a ball that interacts with the air through convection, and the heat transfer coefficient and surface area are passed to the convection model. The air has a temperature that can be controlled. So translating this to a Modelica model will look something like this. We have the step and constant values. that will pass the surface area and heat transfer coefficients. We have the product to multiply them, and the product is passed to the convection model. And here we control the air temperature using a step, and that is converted into Kelvin and assigned to the prescribed air temperature component, that is the air. Now that air temperature interacts with the other node of the convection component, and the solid interface connects with the heat capacitor. Now, one point that you noticed is that in our problem statement, we had a ball of radius 2 centimeter, but Modelica takes the heat capacity. So we need to perform certain pre-processing calculations for heat capacitor to find that value. We can say that the heat capacity is mass times specific heat, and mass is rho times volume, and volume is 4 by 3 pi r cube. So performing the calculation, we can see that volume is calculated, mass is calculated, and finally multiplying with specific heat, we get the heat capacity of this particular component as 132.159 joule per Kelvin. Similarly, for thermal conductance GC, we can say that GC is H times A, and A is 4 pi r square. So for cooling, we have the HTC value of 45.09, and for heating, we have the HTC value of 78.23, and the surface area being 0.00502 meters square. Now to translate this into the form where we need in our step component, we can say that the transition happens at 900 seconds, and initially during the heating phase, our value, that is before the start time, our value is 78.23, and after the start time, the value is the difference between final and initial. So it is the final value minus the initial value, which is negative 33.14. So we can assign these values to our model. Now let's build this in Open Modelica. At startup, this is the welcome screen that you will see. In order to create a new model, we can use the new button here. Already you can see the Modelica standard library is preloaded. So let's start building. We can click a new model. It creates a new model. The default specialization is model, which we are going to use currently. I'm naming the model as ball heating cooling. Now I'm not going into the details of this, but let's leave all of them at default. We will cover the details of what all this means in later sessions. Clicking OK will create a new component. We have a diagram view and we have a text view. So the diagram view shows an empty screen, whereas if you go to the text screen, you will see that the model is already created with 0 parameters, 0 variables, and 0 equations. It is a bare framework of a model. Now we can start adding our components into this model. So let's go to the thermal library. Here we can see heat transfer, components, and we have the heat capacitor. I will drag and place it here. So it is a good convention to name your components appropriately so that later during post-processing, it will be easy to get them correctly. So clicking OK, we have the heat capacitor. Then we need the convection model. So I will leave the name as convection itself. Now within this one, we have sources and we have a prescribed temperature. So this represents the air medium. So I will just name this as air. Now, one thing is that here you can notice the heat port of convection is on the right, but for the air also the heat port is on the right. One way could be to draw a connection like this by dragging, but which is not very elegant. So we can right click on the component and go to flip horizontal. That means the left and right will be flipped. Clicking this will result in aligning the heat ports. Same way, the heat capacitor has a bottom heat port. Here we have a left side heat port. You can right click on this. Then you can say that I want to rotate this anti-clockwise by 90 degrees. This aligns the heat ports properly. Now we have one more component, that is the conversion from degree Celsius to Kelvin. So we can go to heat transfer Celsius section, then to Kelvin, can drag it here. Then let's leave the default name. Here again, the model is oriented from left to right. I can flip it horizontally by either pressing the H button on keyboard or by clicking from the right click menu. So we have all the components required from our thermal library. Now let's go to the blocks section and take the remaining components. We need the sources. We need a constant value to represent our surface area. So I will name it as surface area. Now I need a step that will represent the heat transfer coefficient. I will name it as HTC, short form for heat transfer coefficient. So we have two values. Now I need one more step for my air temperature. So I will just mention this as air temperature. I can flip it again from left to right using the right click menu. So we have two parameters, but this was only one thing. So the thermal conductance is the product of heat transfer coefficient and surface area. We can go to the math subsection and take product and place it here so that we can connect our heat transfer coefficient and surface area together and get the output as their product and connect it to the convection component. So you can start clicking on one interface and drag your cursor towards the other component and leave it there to establish a connection. Okay, so like this, we can click between each component and establish connections. So all our connections are properly established now. Now let's parameterize them. So from our previous calculations, we could see that the heat capacity of our capacitor is 132.159 joules per Kelvin. Let's add it here. 0.159. So this is the heat capacity, which is marked as the product of mass and specific heat capacity. Now in our problem statement, we saw that the ball is initially at a temperature of 25 degrees Celsius. So the T start value is the initial temperature of the ball. So this can be changed in unit, but since we have the value readily available in degrees Celsius, I'm going to leave it as default. Clicking OK will set it. Now you can see the parameter value is highlighted here. Same way, for our surface area, we saw that our surface area is 0.00502 meters square. Let's bring it up here. We have the constant value, which will remain constant throughout the simulation. I can plug it as 0.00502. Now, coming to the heat transfer coefficient, we saw that the offset value is 78.23, height is minus 33.14, and start time is 900 seconds. So let's assign them. We have the height as minus 33.14. We have the offset as 78.23 and the start time as 900. So we have characterized the convection part. Now let's set the air temperature. So air temperature also changes at 900 seconds. So our start time will remain same. So initially the airstream temperature is very hot. It is 200 degrees Celsius. So we will set the offset as 200. Now our final value will be 20 degree. So converting from the 200 value, we have 200 and 20. So the difference is minus 180. So either we can provide it as minus 180, or even easier, if you don't want to do the calculation, you can directly plug in expressions. So you can directly type 20 minus 200. So that is our final value minus initial value. That is the height. So you can plug this and start time is in seconds. That is 900. Clicking OK. Now we have characterized all the components that are needed for our simulation. Now, if you want to highlight, if you want to keep it more cleaner, you can use the fit to diagram button here to reassign your frame so that all your components are well captured within the frame. Now, another convenient method in Open Modelica is the text annotation. So you can click here, it will generate a text. You can scale it up and down depending on your requirement. You can type that product of heat transfer coefficient and surface area to clearly communicate what this means. So this can be very useful when we are building very large models. When you want to explain something within the model, you don't need to create a separate documentation. You can write contents directly into your model without affecting any of the calculations. Now our model is ready to be simulated. Let's set up the simulation. Now, one important thing before we go in here is to save your model. Unfortunately, I should have told this in the beginning. It's always a very good practice to save your model before starting any detailed work. So I can save it with the same name as the class, which is a good practice, but it necessarily doesn't need to be the same. If you want, for a particular reason, if you want to save it with a different name, you are okay to save it with a different name, but always recommended to keep the class name and the file name as same so that it is easy to refer later. So I'm saving it in a location in my computer. I will just save it. Now we have it all set up. It is saved and we will set up our simulation again. Start time is 0, stop time is 2100 seconds, and intervals is also I'm setting as 2100, so every second will be simulated. I have set up the save experiment annotation and simulate. So if I click OK, this will be simulated. Let's see what happens. So the simulation initialized and simulation finished successfully without any delay, and we can see some of our parameters are popped up on the right side. So between modeling and plotting, like we can switch on the bottom right corner. So after simulation, the software will automatically take us to the plotting window. Here we can see our parameters. So let's take the ball, which is our heat capacitor, and we can see there is a temperature T parameter here with a starting value of 25. If you click on this icon, you will see that we are getting a very familiar pattern which we saw in our previous simulation. So we had the maximum temperature as 187.6, sorry, 187.8, believe. So let's verify this with our previous results. So we had 187.9 and 41.44 as our maximum and final temperatures. This was the trend we were seeing. The maximum was attained at 900 seconds and the final attained at 2100. Switching back to Modelica, we are seeing the exact same trend, 44.1 and 187.7. But let's plot them together. So I can open the previous model which we developed in our previous video. Let me just pull it real quick. This is the model which we simulated in our previous video. We have the values set up, equation set up, everything is ready. And it is simulating for a period of 2100. I can run this real quick. So we can compare the two results together. So the ball heating cooling is our current model. The heating cooling is our previous model. So if I take the T ball, which was our ball temperature variable in our previous model, I can overlay it on top of the current simulation and we can see that they're aligning pretty very close. So even if you zoom in, you can see that maximum temperature is aligned very well between the two. So we have exact results between the two simulations built using the text-based approach and component approach. Also, you can see that the air temperature is changing at 900 seconds from 200 to 20. The same can be realized here as air temperature. Since this is in Kelvin, currently we are seeing an offset. You can click on that unit section. From the drop down, change to Celsius. Now you can see both T air and air T are aligned. So this shows that the same model, the exact physics can be modeled in two different ways using building the equations from scratch as a standalone model or using the existing components from Modelica standard library. The first one is easy for smaller models, but when it becomes larger models, building every equation from scratch often leads to errors and incomplete models. Now, one limitation we found in our current approach is that we have to do quite a lot of pre-processing calculations to get the parameters required for our model. It could be nice if there is a way we can automate this process also as part of our model-based building. In our next video, we will see how we can extend existing Open Modelica models to build our custom equations into them. So that's all for today. Let's recap what we learned. So this, I'm not adding anything new since we are taking the same problem statement. But from a Modelica standpoint, we understood what is Modelica standard library, the graphical components, interfaces and connectors, parameters, calculation, setting up and running a simulation, and results comparison. I encourage you to experiment further with the components from standard Modelica library. We will see you again. Till then, happy modeling.